Anthony, we're here in Vieques, Puerto Rico at the FQXI Physics of Information workshop. I've enjoyed it very much. If we had to define the physics of information, where would we start?
There are a lot of places to start in thinking about information. And I guess I would start by sort of reminding people that physics almost is entirely about information. So if you think about quantum mechanics has these wave functions or states, and it's got this mathematical apparatus for evolving the states, and then you take the state at the end and it gives you probabilities for things. So what is the state? It's a information about what results you're going to get when you do measurements in the future. And that's what the state is. That's all it is. But then if you ask a physicist what is an electron, they'll say, it's a particular quantum state. Well, what is a molecule? It's a more complicated quantum state. So everything is a quantum state. And quantum mechanics tells you that a quantum state is information about what's going to be measured later. So everything is information about what's going to be measured later. What does the measuring? Other stuff that's quantum states. So in that sense, in a real way, quantum mechanics tells us that everything is information about other information about other information. And even if you think of general relativity, the theory of space-time, you think it's very solid, it's got stuff, it's got space-time, but it can be shown that general relativity is essentially a series of causal relationships. What's a causal relationship? It's what regions can send information to what other regions. So most of the description of space-time is about information transport. Where can it go? Where can't it go? And a little bit extra information about how big things are. So half of general relativity, I would say, is also about informational relations between things. So the two sort of pillars of physics, general relativity and quantum mechanics, both are either entirely or largely about information looked at in a particular way. And so I think it's almost hard to say what is the physics of not information.
When you're using the term information, particularly physics of information, are we talking about it in the technical sense of a binary piece of information, an on, off, 0, 1, there, not there, or a more general sense of knowing what it is?
Information is one of these very, very tricky words in physics because there are so many different meanings to it, and everybody thinks that their meaning is pretty much the same as everyone else's meaning, and it's not. Entropy is another word that's just like this. So what I like to think about are, first of all, try to talk about the particular sort of entropy that I'm interested in, and then define information in terms of that entropy. So for example, there's so-called Boltzmann entropy that tells you, well, if I have some system and it's got lots of microscopic states, lots of very individual configurations it could be in, we can only know macroscopic information when we measure things. So we attribute an entropy to it, which is the number of those individual microstates that are compatible with the information we have about the system. So that's the so-called Boltzmann entropy. And that's the kind of entropy that increases with time in the second law of thermodynamics. Now there are other sorts of entropy. There's the so-called Shannon entropy, there's the von Neumann entropy, that are related in complicated ways to the Boltzmann entropy. So as soon as you say entropy, if you haven't said Shannon or Boltzmann or von Neumann, you've already confused the other party, or vice versa. Now once you've got an entropy, I generally like to think of information as the gap between the entropy that a system has and the maximum entropy that it could have. So if you think of a system as totally disordered, you know basically nothing about it. It's got maximum entropy, and you've got no information about it. And if you measure some things about it, or if you just know more stuff about it, you have narrowed down the possible set of states that are compatible with what you know. So its entropy is lower, and you've got some information about it. And that information you can think of as the gap between the entropy and the entropy that it could have. So I look at information that way, and so for each definition of entropy that you have, you've also got a type of information. You've got Shannon information and von Neumann information and Boltzmann type information and so on. So what's also frustrating about information is that it's so useful. So all these different types of information are really useful in different ways.
What's
So
an example of that? How are each one of those useful?
if you want to talk about, say, the second law of thermodynamics, the way to understand that by far the most easily is to think of Boltzmann entropy, because you think of, if it has a low entropy, it's just in this very particular corner of the state space that it could be in. And then as it evolves away from that, it's almost inevitably going to go elsewhere into a larger entropy region. So it's fairly easy to see how the second law works there. Now, if you look at the Shannon entropy, or the statistical entropy, or the von Neumann entropy of a system, suppose you know exactly what state the system is in, or even if it's in a particular combination of those. Turns out the entropy, if you don't do anything else, stays fixed. The entropy doesn't increase. So that entropy is useful for certain calculations, but it's not the entropy that increases with time. And so you have to be very careful in distinguishing them.
And so overall, how important is understanding information as a kind of a foundational concept to the doing of modern physics? Because it's fairly new where information is so important in physics.
I think there are a lot of things in physics that you can avoid the use of information and information theory and entropy to describe, but it gets much harder. So take, for example, the so-called black hole information loss problem. This is the problem that if you throw an encyclopedia into a black hole and then let the black hole, wait for the black hole to evaporate by this Hawking radiation process, that Hawking's calculation tells you that pure thermal radiation comes out that doesn't contain any information, whereas your encyclopedia clearly did. So where did that information go? What that specifically conflicts with is a sort of basic tenet of quantum mechanics, which says that that sort of microscopic information never goes away. So you have to choose one of several unpalatable alternatives to deal with this paradox. Now, you can pose that information loss paradox and some of the other ones that people think about in terms of black holes in non-information terms, but it's very hard, and it's also not quantitative so much. Like, you can say the theory tells us that black holes aren't unitary. They break this unitarity thing in quantum mechanics. But unitarity is either you got it or you don't. Whereas if you're thinking about information loss, you can ask, well, how fast can the information get out? Does it work if it gets out this fast? How much information is in the Hawking radiation? So you can quantify things in a way that's very hard to do if you can't use those information theoretic concepts. So while I think there are probably ways to avoid thinking about information in physics, it has turned out to be tremendously useful as a sort of foundational concept in which to couch things.